Picking back up with Chapter 6, we're going to talk about what are called quantum numbers, and specifically we're going to look at those that describe what are called shells and subshells.
All right, so we know that electrons are in orbitals, and if you really want to, you can solve what's called the Schrödinger equation, and you can obtain an equation that describes that orbital, and it is shown here at the bottom. This is ridiculously complicated, right? There is so much here. There's maybe some recognizable math. We got some factorials, some exponents, but there's a lot of variables that we would need to learn. There's also some equations that are hidden in here. So it's kind of layered stuff. It's just really complicated. And more importantly, it's so mathematical, it doesn't give any sort of chemical insight that's really what we care about. So instead, what we want to do is look over here and we can see there's N, L, and M. And if we look on the right-hand side, those letters do show up. So these are what are called quantum numbers. And the whole idea of a quantum number is a number that has a value that is related to the property of, or the actual orbital shape, the actual equation of the orbital, but it's going to be easier to deal with, and it's going to inform what the orbital looks like. So instead of talking about the actual equations, what we're going to do is talk about the numbers that go into the equations and how that affects what the orbital looks like, and that kind of stuff, what comes out the back end. So if I want to describe an electron, I need 4 quantum numbers. Every single electron requires 4 quantum numbers to be completely described. What the orbital is, where the electron is, all that kind of stuff, characterizing that state. We need 4 of them. So we'll work our way through what those 4 types of numbers are and what their values can be. So the first quantum number is the principal quantum number, which is a lowercase n. Usually you see it italicized. You can see I forgot to right here. It's not always going to be italicized. That's kind of generally true for quantum numbers, that usually they are italicized, but a lot of times people don't, or in different contexts, don't italicize them. Or bold kind of stuff, one or the other, just kind of indicate it's a special value. So the principal quantum number, which is little n, describes the shell where the electron is located. So this idea of calling it a shell, this is the first thing, the first indication we see at the point of these quantum numbers is not only going to be to describe what the orbital is, but they're also used as kind of an address for where the electron is. So we're going to kind of organize the arrangement or the distribution of electrons in an atom using these different kind of organizational groupings, and shell is the largest grouping. So, you know, electrons can be in shell 1, 2, 3, whatever. And so n, the possible values of n is any positive integer. N can be 1, 2, 3, 4, 5, 6, keeps going, sky's the limit. And so we've actually seen this before in the Bohr model. Energy only depended on n, right? There was one possible value, just n, you know, it was 1, 2, 3, whatever, the orbits that he was counting. And so it's the same idea of, you know, the kind of the closest level and then so on and so on. We know there's a little more structure to it than that, but we can certainly see what it looks like. All right, the second quantum number is the angular momentum quantum number. The angular momentum quantum number has the symbol of L. Technically, it's just a normal italicized L, but I cannot draw that or write that, so I use a swoopy L. So the swoopy L is always going to mean the angular momentum quantum number. You'll note this has kind of come to other parts of my life. When I write L's, I use swoopy L's now, but that is from this quantum number. This describes the subshell where the electron is located. So N was the shell. That would be something like state that the electron is located in. Subshell would then be something along the lines of, say, city, right? So that's the city where the electron is located in. It's a lower level of organization, smaller, there are fewer things in it, subshell. The possible values of L depend on the shell that you're talking about. So what is the value of N determines what the possible values of L can be. So L goes from 0 up to n minus 1. And you count those up by 1, so 0, 1, 2. So whatever the value of n is, you subtract 1. That is the maximum possible value for L. And the lowest possible value for L is going to be 0. So you can have a 0. So if we want to look at some examples of kind of this translation or of what that all looks like, we can see that we start off with, say, n equals 1. That's our lowest possible value for 1. So L goes from 0 up to n minus 1. if n is equal to 1, 1 minus 1 is 0. So L goes from 0 up to 0. So there's just 0. Okay, that's the only possible value for L when n is equal to 1. Our translation of that is that there is one subshell in the first shell. N equals 2. Now 2 minus 1 is 1. So L can be either 0 or 1. That means there's two possible values for L. That means there are two subshells in the second shell. N equals 3. Now L can go up to 0, 1, or 2. 2 is 3 minus 1. So that means there are 3 subshells in the third shell. Okay, so in that third shell, there are 3 total possible subshells. All right, so subshells are named with specific letters corresponding to particular values of L. So this is where our L quantum number has numerical values, 0, 1, 2, 3, whatever. But there's going to be an interpretation of this where we're going to take, say, L equals 0, and we're just going to call it S. Okay, so there is a letter that corresponds to values of L. So L equals 0 is S, L equals 1 is P, L equals 2 is D, and L equals 3 is F. You will note these are totally not alphabetical. There's nothing about it, but these are the most commonly used symbols. These are going to be the most helpful for you to learn. These symbols, the name, the SPDF, come from experimental results. So for example, S means sharp, P means principal. So they correspond to results from taking, heating up atoms and seeing the lines that come out. Some of the lines were sharp, some of the lines were the principal lines, those sorts of ideas. SPDF, those are going to be the most helpful that we're going to use most oftenly between 0, 1, 2, 3, SPDF. After you hit L equals 3, you go to 4, 5, 6. You can keep going. There are symbols for these higher values of L, G, H, I. They just go alphabetically. We're not really going to use those. Those aren't really commonly used in stable atoms. If you start to get up into looking at those excited states, when you put the atom, say, in a flame, G, H, and I start to matter. Or doing some other fancier things, those matter. But for the most part, we're not going to use those that much. But it is possible. We have explanations for how these things work. Okay, so the purpose of doing that translation is we want to be able to combine subshell symbols to make names of subshells. Okay, so for example, I have n equals 2 and L equals 1. So those would be two values for my quantum numbers. And so the L characterizes the subshell, right? So, you know, how we could say it is the L equals 1 subshell in the second shell, but that's really clunky. And in general, we prefer not to use that language. Instead, we call it the 2p subshell. So the purpose of using these letters is to name the subshells that are indicated by the L quantum number. So 2p subshell, 2 in front means you're in the second shell. You know that n equals 2. P always means L equals 1. So you put them together. You've basically combined this whole long statement out here into just n equals 2, L equals 1, 2p. Okay? If say n is equal to 3 and L equals 0, we'd call that 3s. Or n equals 3 and L equals 1, we call 3p. Right? So we can go through these sorts of analyses. N equals 2 and L equals 0 is 2s. So one of the things you'll note is that when we have that L equals 0, it's always S and S. Right? So that letter always has the same interpretation for the L quantum number, independent of the number that's in front of it, that N quantum number, which is the shell. So there's always S subshells in any given shell. It doesn't matter which one you're in. All right, so we want to be able to get some practice going from these quantum numbers into my subshell designation. So N equals 3 and L equals 2, N equals 2 and L equals 1, N equals 4 and L equals 0, N equals 4 and L equals 3. So we've got paired of possible quantum number combinations. That's the long form interpretation. I want to take those and turn them into a subshell name. So if I want to do it, I know that N, the two pieces of information are N and L. N, the shell, is just the number. That number stays. L value is where we have to interpret it in terms of the letter, right? What letter corresponds to that value of L? So first off, we'll look at N equals 3, L equals 2. That N equals 3 comes across, we get the 3. Then the L equals 2, we interpret, that gives us the D. So N equals 3 is the 3, and then the L equals 2 is the D. So anytime we have a D, we know that L equals 2. So we'd call that the 3D subshell. N equals 2 and L equals 1, well, we're going to keep, we could saw previously, we just keep, whoopsies, we keep that number for the number, and then we just need to interpret L equals 1. And L equals 1 is P, so that is a 2P. N equals 4, we keep the number. We need to interpret L equals 0, so that is S. So this is called 4S. N equals 4, again, we keep that. L equals 3, we need to interpret the letter. L equals 3 is F. We note it's still 4F because the N has the same value, so that all stays the same. So we do want to just be a little bit careful when we're naming subshells. We have SPDF, 1, 2, we can do all this translation now. But just because you can name a subshell doesn't mean it actually exists. There are restrictions on the possible quantum number combinations. We want to be sure that we maintain those. So for example, 1P, right? I know I can just say that. 1P, that would mean N equals 1 and L equals 1. So that'd be my 1P subshell. But the thing is, L, possible values, goes up to N minus 1. So if N is equal to 1, 1 minus 1 is 0, the highest possible value for L is then 0. So 1P is impossible. L, the value for L, must be less than the value for N. It can't be the same, and it can't be greater. So if we look at, for example, 2F then, N equals 2, L equals 3. That should be an immediate red flag that that L value is larger. That is impossible. When N equals 2, L can only be 0 or 1. So 2S and 2P are allowed. 2F is not allowed, nor is 2D. Only 2S and 2P. There are only 2 subshells in the N equals 2 shell, in that second shell. So what is allowed, right? Let's kind of put it all together. When N equals 1, L can only be 0. There's only one subshell in the first shell. The symbol for that then is going to be 1S. If you bump up N equals 2, now you can get 2 subshells, 0 and 1. Okay? And so the 0 again is interpreted as an S, but this time it's 2S, and the 1 is interpreted as a P, so we get a 2P. N equals 3. My allowed values for L are now 0, 1, and 2. I have 3 values when N equals 3. We can see that it's the same number of possible values of L is just equal to the value of N. So that 0 is still an S, so it's 3S. The 1 is still a P, 3D. And then we get the 2, we get up to 3D. So I get the 3S, the 3P, and the 3D.